Today we're going to start a series of videos on what's called the method of images. So we're going to start by figuring out the classic image problem, and that'll set us up for the next few videos. We'll start by drawing an infinite plane that will be conducting and grounded. So when I say grounded, I mean that the potential at this plane will be set to v is equal to 0. We'll draw our coordinate axis in such that z is in the up direction, x is in this direction, and y is in this direction. So we have our infinite conducting grounded plane, and we'll place a point charge, positive q, at some distance d above the plane in the z-axis. That means that this charge will have coordinates 0, 0, d. So 0x, 0y, and d in the z direction. And what we want to do for this problem is to figure out what is the potential v in the region z is greater than 0, which is the region above the conducting plane. Usually for the potential, we can just use the formula 1 over 4 pi epsilon naught q over r, where this vector r is the direction or the distance to the point charge that we're considering. However, in this case, this is challenging because the conducting plane will change what is the charge distribution, and we'll have a potential produced by the plane as well. But this is hard to find because we are not sure what is the charge distribution, nor what is the total charge induced on this plane. So instead, what we're going to want to do is we're going to want to take Poisson's equation, which says that the Laplacian of the potential v is equal to negative 1 over epsilon naught times the charge density rho. And we're going to want to solve this equation with the boundary conditions saying that v, our potential v, is equal to 0 at position z is equal to 0, which is what we said here when we said the plane was grounded. And we want to say that v goes to 0 as our position extends to infinity. And that is stated by saying that x squared plus y squared plus z squared is much greater than d squared, where d is the distance of the charge away from the plane. So as our position extends to infinity, our potential will also extend to infinity. So using these two boundary conditions and Poisson's equation, we'll be able to figure out what is the potential in the region above the plane. So the goal of this problem is to determine the potential v in the region above the plane where z is greater than 0. And we can do that by solving Poisson's equation and remembering that the first uniqueness theorem says that once we find one potential v that satisfies this equation, this is the only v that will satisfy the equation. The first uniqueness theorem has a corollary which states that the potential is uniquely determined in a volume v if the charge distribution is completely specified and the potential is specified on all boundaries. In this case, we have a single charge, positive q, and an infinite conducting plane, and that will be our charge distribution. And the potential v is equal to 0 as z is equal to 0, and v goes to 0 as x squared plus y squared plus z squared is much, much greater than d squared. And these are our boundary conditions. This specifies the potential on all boundaries. So using these two statements, we can remember that the potential v that we find that satisfies this problem will be the only solution to this equation. And if we're able to, by somehow changing the setup and solve a different problem to find the same v, this will be the only v that satisfies the equation. So instead of solving this complicated problem where we aren't sure what the charge distribution is on the plane, we can solve a simpler problem and use the same v to find the solution to both problems. So instead of solving the potential for that challenging problem where we had the positive charge above the conducting plane, we'll set up a different problem where we have two charges, positive q and negative q. And we'll determine the potential of this charge distribution and use that in order to solve Poisson's equation. So we'll draw our z-axis like so, and our xy plane centered on this charge distribution, such that positive q charge is a distance d above the xy plane. So it's that position 0, 0, d. And the charge negative q is a distance negative d away from the plane, such that it's position 0, 0, negative d. What we want to do is we want to figure out what is the potential of this charge distribution. We can do that by remembering that potentials add linearly. So if we find the potential of each individual charge, we can add them together to find the total potential of the charge distribution. We'll start with a general form of potential equation, which says that 1 over 4 pi epsilon naught times the charge q over the position vector r of where the charge is actually situated in our Cartesian space. So if we use this equation and apply it to both the positive charge and the negative charge, add them together, this will be the total potential of our charge distribution. So we'll start with V plus, and we'll say that it's equal to 1 over 4 pi epsilon naught times our positive charge q over x squared plus y squared plus z minus d squared, all square rooted, where this is the position vector of our charge positive q, a distance d above the z-axis. We can find similarly for the negative charge, we have 1 over 4 pi epsilon naught times negative q, where now we include our negative charge, x squared plus y squared plus z plus d squared, where the plus d comes in because now we're at a distance negative d below the xy plane. So with these two potentials, we simply add them together to find that 1 over 4 pi epsilon naught. We can pull the q out because q is common between both if we say that it's the same magnitude. And we can say that it's x squared plus y squared plus z minus d squared, square rooted, 1 over minus x squared plus y squared plus z plus d squared, square rooted 1 over. And so this is the potential of this charge distribution, where we have a positive charge, a distance d above the xy plane, and a negative charge, a distance negative d, just below the xy plane. So now that we determined what the potential V is for this charge distribution, we can check it with our previous boundary conditions. Our previous boundary conditions said that the potential V was equal to 0, at position Z was equal to 0, and that potential V went to 0 as x squared plus y squared plus z squared became much, much greater than d squared. Essentially, as our position that we're looking at becomes much, much greater than the place where the charge is situated in our space. We can check the first boundary condition, which says that when we set z is equal to 0 in this potential, we should get v is equal to 0. Let's check it. So q over 4 pi epsilon naught, big bracket, we have x squared plus y squared plus 0 minus d squared, which will just give us negative d squared, which of course is just positive d squared, but we can leave it like so for now, 1 over, and we're going to subtract off x squared plus y squared plus 0 plus d squared, so we get a plus d squared and a square root, 1 over. So by looking at these two terms within the brackets, we can find that because negative d squared and positive d squared give the same value, this term will cancel out and just become 0. So v is equal to 0 when z is equal to 0, and the first boundary condition is satisfied. So now we can look at the second boundary condition, which says again that our position x squared plus y squared plus z squared becomes much, much greater than the distance that our charge is away from the plane, and the potential should go to 0 as this occurs. So by plugging it into our equation above, we say that q over 4 pi epsilon naught, big bracket, and in order to express this here, essentially d is going to become negligible compared to the other terms. So we end up with simply x squared plus y squared plus z squared on the bottom, and we can ignore the d because it's much, much less than x squared plus y squared plus z squared. And in this term, we get the same thing, x squared plus y squared plus z squared. So once again, we see that within the brackets, these two terms will cancel, and we end up with v equal to 0 as x squared plus y squared plus z squared becomes much, much greater than d squared. So this means that our second boundary condition is also satisfied. So we refer back to the charge distribution which we started with at the beginning of this classic image problem. We find that in the region z is greater than 0, we have a single point charge, positive q, a distance d above the xy plane, and in this setup, above an infinite connecting grounded plane where the potential v is equal to 0. If we look at this setup above, we see that in the region Z is greater than 0, we have the exact same charge distribution, where positive Q is the only point charge at distance d above the xy plane. And that, in conjunction with the fact that our potential V that we found for this setup above satisfies both boundary conditions set out by this boundary, by this problem below. What that means is that because of the first uniqueness theorem, this potential that satisfies both boundary conditions and the same charge distribution will be the same potential as for the setup below, but found by simpler method. So if we say that V is equal to Q over 4 pi epsilon naught, big bracket, x squared plus y squared plus z minus d squared, all that in square root, 1 over minus x squared plus y squared plus z plus d squared, all square rooted, 1 over closing bracket. So this is the potential that we found for the charge distribution set up above here, where we had a positive and a negative charge. And we can say that it's the exact same potential as for the setup below in the region where z is greater than 0, because the charge distribution is the exact same in both setups, and also the boundary conditions are satisfied by the potential for both problems. We don't really care about the region below the plane, because that wasn't what the initial problem was set up to be. So in that case, we don't have to worry about the charge distribution z is less than 0, because of course in this case it will be different. Because we only care about the region z is greater than 0, this is the potential produced by a positive charge q at distance d above an infinite conducting grounded plane.